Good afternoon, everyone. How is the transmission?
Good.
Am I audible?
Clear. Clear.
Yeah,
Excellent.
absolutely.
Excellent.
Clear.
Wonderful. Welcome, everyone, to the second webinar in a series of webinars. I'm happy that all of you are here. Today, we're going to talk about a feature called Auto-Splay in MAPP XT. But before doing so, I think it's always nice to briefly go through the Zoom controls and in an attempt to coordinate today's webinar. So I'm going to share my screen. I'm going to take you to the PowerPoint of today. And there we go. So as I said before, we're going to talk about Auto-Splay today. And we're using the Zoom platform to do so. Apologies if sometime I appeared a little bit distracted. I'm only managing several displays. We're going to use Zoom, and all of you are expected to have a window not unlike the one you see in front of you. In the bottom left corner, you have the possibility to unmute your microphone. If you click this button, the button to the right of it allows you to turn on your camera if you desire to do so. But I expect most of you to make use of the so-called chat and participant feature. If you click on participants, a window opens to the right-hand side, which shows all the fellow attendees that are joining you on this call. And if you click on the chat button, you get something which is pretty self-explanatory, which allows you to address the nation by entering a message at the bottom of the screen. Or you can also, if you see somebody in the list of participants that is familiar to you or a colleague, you can also address individuals and send private messages. In an attempt to coordinate your questions, you can see that there's a button over here that says raise hand. I will do the best of my abilities to keep track of that, but I would also like to remind you that I'm all alone, and right now there's over 200 of you. So do not be offended if I do not manage to address all your questions at once. That being said, as always, this is not going to be a monologue. As far as I'm concerned, it's going to be a dialogue, and that means that if you have a question, raise your hand. I'll try to notice it and address your question to the best of my abilities. We will try to keep it under 1 hour. But these things are kind of dynamic, so who knows? Okay, so Auto-Splay, a feature in MAPP XT by Meyer Sound. So what will you learn during this webinar? We'll start with some exercises such as how to determine the coverage angle of a loudspeaker. And today we'll use an X40 to do so, because we need to be on the same page in identifying coverage. Then we kind of briefly look at the difference between a constant cue behavior versus a proportional cue behavior. I noticed that I made a typo. Sorry about that. It should say proportional cue. Briefly going to look at the differences between beam narrowing and beam spreading. Then we're going to look at the various splay angle options that live within the Leo family's products. We're going to do a demonstration in MAPP XT with LEOPARD. And then we're going to look at how to insert an architectural visual aid, which we need. We're going to assign that architectural visual aid, and we're going to activate it as a listener plane, which we require for the Auto-Splay function, the algorithm to work. There are some constraints to be mindful of, which has to do with inclinations, as we're about to investigate. Then there's the option to assign target zones, why overshoot is advised, and how to go about multiple listener planes. This is what I intend to cover today within the next hour at most. Okay, We will be using MAPP XT, evidently, which you can download for free at the Meyer Sound website. For those who do not already have a copy of the system design tool, it's the proprietary software that we use for designing sound systems and such. And that is the program that I intend to use today. The first exercise that I would like to look at is the exercise of determining the coverage angle of a loudspeaker. And today I intend to use the Ultra X40, which has a horizontal coverage angle of 110 degrees, as you can see over here in the close-up, and a vertical coverage angle of 50 degrees. I'm only going to do the exercise in the horizontal plane, and I am 100% confident that you will be able to replicate the exercise in the vertical plane as well. So without further ado, let's go away from PowerPoint and let's go to MAPP. Then one will come later. This one comes first. I'm also gonna want to make sure that all microphones are muted. So let's make sure that that is happening. Okay, so this is MAPP, and right now we see part of a polar plot. In the bottom of the screen, we have the horizontal dimensions. That is the x-axis in meters. On the left, we have the vertical dimension, that is the y-axis, also expressed in meters. And right now, we see about 1/4 of a polar plot, or a quarter. I'm briefly going to show you the entire picture so that we just know what it is that we are talking about. So I'm going to make this -33, -33, 66, 66. So this is the entire picture. We're basically looking at a huge polar plot. In the center of our polar plot right now, there is a single loudspeaker living, which is one instance of the X40. You're looking on top of the X40. As always, if you click on a loudspeaker, you can edit its properties, and the properties will show you that right now we're looking at it from a horizontal point of view rather than a vertical point of view. This is what the loudspeakers expect to look like when observed from the side with a section view, but for today's exercise, we're going to look at it from a plan view. And by default, if we're going to look at a picture, let's say 1 octave, by default, if we press predict, then MAPP XT will show you a beautiful gradient ramp. I like to think of these as jet colors, where red is hot and blue is cold or soft. And we see this resembles a little bit the wing of a butterfly. We see that something is going on over here. We see an SPL plot, and it has these wonderful colors. The problem is that if I want to use this kind of display, it's really hard to figure out where discrete steps lives, because if we're looking at a coverage angle, when we talk about a coverage angle, what is it that we're talking about? When a data sheet says this loudspeaker has 110 degrees of horizontal coverage, then it means that we're talking about the coverage angle between the -6 dB points. So we're going to look for 6 decibels of angular attenuation, and that's going to give us a slice of pizza, and we want to determine the size, the angle of that slice of pizza. And in order to see that, having these beautiful colors doesn't serve a purpose. So what I propose is that we go to our settings, and we go to the SPL palette, and rather than choosing 265 colors, we're going to intentionally choose to have MAPP show us 3 dB per color. And if I do that, I will have to make a new prediction, but now we get something which is more defined, and we can better tell what is going on. So what you need to understand at this point is that that every color change that we have over here on the right hand side now represents a 3 dB drop in level. So if you go from orange to yellow, you lose 3 decibels. If you go from yellow to lime, you lose another 3 decibels. And what is even more important, and for this, since it involves a symmetrical shape, whatever this shape looks like, but it's symmetrical. And in order to make you appreciate this a little bit more, I propose that to get the best possible resolution, that rather than looking at the entire thing, I propose that we look only at a quarter of it, and then I'm sure that we have sufficient imagination to understand what the other half looks like. So right now we really have a crisp picture, and we can really see what is going on. So if you look at the scale on the right hand side, okay, then every time you go from one color to the next color, you lose 3 decibels. Okay, that is what it means. But the thing that is really interesting at this point are the so-called isobars, or contours that separate the colors from each other. So this is a contour. It's a transition between light blue and dark blue. Okay, and I'm trying to trace it. This is a contour which is between a darker blue and an even darker blue, and this is a contour or isobar, if you will, and this is a contour or isobar. And what you need to know about those contours or isobars is that those are the positions in space where the loudness is equal. So if you were to walk along this line, you would experience the same level at the frequency range of interest, which is currently 1 octave, an 1 octave interval centered at 8 kilohertz. And the same is true when you walk this line. If you were to walk this line in plan view, you would experience, for those frequencies, you would experience the same level. And it goes without saying that the same is true for these frequencies as well. Now, what we're going to look for is we're going to look for 6 decibels of angular attenuation. That is the stop condition. Once we see 6 decibels of angular attenuation, we have hit the edge of coverage, and we're going to look at how many degrees that is. And in order to help myself in the process, we have these tick marks over here, or these increments, and every increment that we have over here is a 1 degree step. Okay, so the minor tick marks, the minor increments are 1 degree steps. Okay, and the big increments, which is this guy and this guy and that guy, those are the 5 degree increments. So that really should allow us to determine that coverage angle quite accurately. Okay, so I'm done with this. Let's introduce a microphone so that we can also measure the transfer function. So I'm going to go to Insert. I'm going to do Insert Microphone, and that will open up a dialog. And since we're working in plan view, I would like to see the microphone from above to make sense to my brain rather than from the side. So that's the microphone, and let's drop that microphone at 16 meters distance using the X and Y coordinates on axis to that loudspeaker. So I'm going to press play. Okay, boom. So here is that microphone. Let me zoom in using the magnifying glass. Let me zoom in on the region of interest. Okay, and there we go. So on axis to our loudspeaker, this is where the loudspeaker lives. And on axis to that loudspeaker over there, there is a microphone living at a distance of 16 meters. And let's make a picture. Let's make a picture of what our X40 looks like at this distance. So I'm going to hit predict. Numbers will be crunched. A dialog will show up. I'm going to show you that dialog over here. I'm going to go to the frequency response. I'm only interested in the result at this point. Only interested in the result. I'm going to set the delay locator to account for the flight time. What do I mean by flight time? That is the time that it takes the sound to cross the distance between loudspeaker and microphone at 344 meters per second. And over here we see the beautiful magnitude response of a Ultra X40 at 60 meters distance. Notice that this magnitude response is effectively flat, which is to be expected. And as we discussed last week, that it has a phase curve which comes from the PC50 5 to 70 family, informing us that the first wraparound lives between 55 and 70 hertz. But that's beyond the scope of this webinar. If you want to know more about that, be sure to watch the recording of the product integration webinar of last Friday, which you will find on our YouTube channel. So I'm going to store this, and I'm going to store this as the X40 Solo on X, which is an abbreviation to remind me that we're looking at this loudspeaker on X's. And I've managed to keep some traces from previous webinars. I'm gonna clean those so that we get a nice clear picture. I'm going to recall this trace, and I'm going to put it in memory slot A so that I can reference it later on during this explanation. Okay, I'm happy with that. So I can tell by looking at the colors that our microphone lives over here, and if I maintain my distance, which is mission critical for determining a coverage angle, by the time that I come over here, I've lost 3 decibels. If we decide to call the transition between lime and light blue, if we decide to call that 0 dB. Now, why I wrote 0 degrees is a mystery to me. I intended to write 0 dB. It also implies that when we have the next color transition, that we have lost 3 decibels, but what we're ultimately looking for is the next color transition while preserving a distance, and this is the milestone that we're looking for. This is the -6 dB that we're looking for. And I want to measure there. I want to see what goes on. So here's what I propose. Let's select our microphone. Wrong tool. Let's select our microphone, and let's go to the rotation tool, which you can recognize by that weird arrow living over here. It probably has a name, and I have no clue, but I'm going to select it nonetheless, the rotation tool. And now you can see that there is a black circle with a cross in here. That's going to be the pivot point. That's going to be the point of rotation, the center of rotation. And I'm free to choose that center of rotation anywhere I click within the sound plane. And what do you think I'm going to do? I'm going to put that center of rotation at where the loudspeaker lives. Because if I do it at where the loudspeaker lives, I can now orbit the loudspeaker using that microphone while preserving my distance. So there we go. If we call this 0 decibels, then we have lost 3 decibels by the time we get over here, and we've lost another 3 decibels by the time that we've gotten over here. And notice that if I leave the microphone over there, but start drawing an arrow to show you where we ended up, and I go through that microphone, and I go through the all the way to the edge of the polar plot, that we have arrived at, let's count together. Let's count together. There we go. Oops, I did not intend to do that. That is the first 10 degrees, 20, 30, 40, 50 degrees, and another 5 degrees. That puts us at 55 degrees off axis in one direction. And because we're dealing with a symmetrical exercise, it's safe to say that you can also go 55 degrees in the opposite direction. But I want to look, oops, did I make a mistake? Let me see. Looks like I make a mistake. 10, 20, 30, 40, 50. I must have misplaced my microphone, or I'm doing another operating error. 20, 30, 40, 50. 10, 20, 30, 40, 50. 55. Was I mistaken? Wouldn't be the first time. Let's double check. Okay, yes, I was mistaken. Apologies. I rotated too much. So, I'm going to select my microphone, select the rotate tool. I'm going to put the center of rotation at the microphone, and this is where the microphone needed to be. Apologies, for whatever reason, I managed to relocate that microphone. Woo! I'm happy that I caught that in time. So now we go once more. We go to the edge of our circle, and I hope that now I've managed to hit 55 degrees. So there we go. That is the first 10 degrees. Okay, then we have another 10 degrees. Okay, that is 20, and then we go to 30, 40, 50. Now we are at 55. Thank you, and apologies for getting it not right the first time. Okay, so there is the 55 degrees. That is the edge of coverage, depending, assuming derived from this prediction. But now I want to see a transfer function of this. So there we go. The dark blue trace is the measurement where the microphone is currently living. Okay, this is with smoothing, this is without smoothing, but let's see what we're dealing at. One of these divisions on the left-hand side, one of these divisions is 6 decibels. So if you look over here, you will see that from 84, it drops to 78. Those are 6 dB divisions. So if I were to draw an arrow over the peaks of the on-X measurement, and then draw another arrow over where we see these frequencies, where the horn is in charge, the horn of the X40 is in charge, then you can see that all frequencies have dropped by 6 decibels. We call that 6 decibels of angular attenuation, and a proper constant diativity horn does so for all frequencies in its custody. Why do we not observe any angular attenuation at low frequencies? Because the direct radiators at 100 Hz are in the process of producing wavelengths which are considerably larger than the dimensions of the direct radiators or the loudspeaker enclosure itself. And it's a very easy way to prove that. If I show you the entire picture once more, then you will be able to see that there's a vast difference between what goes on at the frequencies in the custody of the horn, which is this picture. That's 110 degrees in total, because we already determined that it's 55 degrees in this direction. Therefore, it's also 55 degrees in this direction. And the combined coverage angle from -6 to -6, that is going to be 110 degrees. And that is why in the horizontal plane, the manual says 110 degrees. Somebody rose his hand. Go for Wes.
Hey Merlin, how do you switch to the plan view so we can try to follow along or do experiments like this within MAPP?
Okay, so plan view or section view, good question, is a point of view, quite literally. If you want to work in plan view, then all your sources should be observed from above, unless you intentionally rotated the sources or changed the sources. So if I go to the edit individual loudspeaker properties, a dialog opens up, and right now I am watching the loudspeaker from above because the cabinet orientation is set to horizontal, whereas if I set the cabinet orientation to vertical and I press apply, then I'm observing the loudspeaker from the side. MAPP doesn't distinguish between one or the other. It's if you set up your MAPP file to work in plan view or if you set up your MAPP file in section view. Does that answer your question, Wes?
Yes, it does. I typically work with line arrays and have never noticed that vertical view for them, but obviously you could just insert a single one that's not flown and get the coverage angle
exactly
from there. Is that correct?
Exactly. Yeah, and we're going to see more of that during the course of this webinar. Okay, question? No problem. Question from Lena? Go for Lena.
Hi. How do you put the lines for the polar view?
Okay, so the lines of the polar view is a CAD drawing, and the next webinar or the one after that on Friday is gonna explain how to prepare CAD drawings for import into MAPP. So
okay, great. Thanks.
If you can make any of those drawings in Vectorworks or in AutoCAD, you can then import them. So that's just a background picture for lack of a better description.
Okay, great. Thanks.
Oh, you're welcome. Okay. So this is the deal at 8 kilohertz, and that is the 110 degrees that you find in the manual and in the datasheet, in the operating instruction and datasheet, or in MAPP for that matter. If we select the properties of our loudspeaker, you will see that the dialog says that we're dealing with an Ultra X40, which is 110 degrees in the horizontal. And just to follow up on my promise, if we were now to go to, like, let's say 125 Hertz, then we will see that this loudspeaker is almost omnidirectional, because now it's in the process of producing wavelengths which are substantially larger than its own dimensions, and it's insignificantly small. So that's how we measure coverage angle. And that's all that I would like to say about that, because we have another 35 minutes to do the thing that we actually here to discuss. So how does this work for line array elements, since we're about to use the Auto-Splay feature? So in Leo families, we have 4 systems, left to right, which is Leo, Lion, Leopard, and Lena. And these are line array elements. And line array elements have a common feature with the X40, which is that at low frequencies, they are omnidirectional. Again, for same reasons, because the enclosure and the direct radiators are insignificantly small with respect to the wavelengths that are being produced. So that is a common trait between the X40 and the line array elements. And if we were to look at a single leopard enclosure in plan view, which you can tell because you see the 2 direct radiators living side by side, then you see behavior that we refer to as constant Q. So notice that that shape that you have over here, even though we don't use 3 dB per color steps, but that shape is very consistent over frequency. It means that the coverage angle remains constant over frequency, and if the coverage angle remains constant over frequency, then the directivity factor, also known as Q, remains constant over frequency, and we refer to that as constant Q. So both the X40 as well as our line array elements are constant Q in the horizontal plane. Their coverage angle within the custody of the horn-loaded section, high frequency section, horn load, is constant over frequency. Whether this is also true in the vertical remains to be seen, because that same Leopard loudspeaker, when witnessed from the side, shows a vastly different picture. Notice what happens with the shape as observed from the side as we go up in frequency. At lower frequencies, we see a shape that is wider, whereas if we go up in frequency, then we see this coverage angle, we see it narrow, we see this beam, if you will, we see this beam being narrowed, being squashed, and that means that this coverage angle is not constant with frequency. As you go up in frequency, the beam gets narrower. This is a single element, mind you, and the vertical coverage angle becomes narrower. It does not remain constant, unlike in the horizontal plane, and we refer to that as proportional Q, because the directivity factor is proportional to frequency. As frequency goes up, the vertical directivity becomes narrower and Q rises, hence proportional Q. And that is mission critical for the inner workings of a line array, because as we're about to discover is that when you design line arrays, you're basically trying to balance 2 mechanisms. Beam spreading is a matter of point and shoot. At 16 kilohertz, it's point and shoot. If you want the sound to go through the 3rd balcony, you just have to send it there. You just have to aim it there. If you want the sound to go to the 1st row at 16 kilohertz, all you have to do is send it there. You have to aim it there. We call that beam spreading. It's point and shoot. But as we're about to discover, at low frequencies, it is primarily the length of the line array that determines vertical coverage. So let's look into that a little bit more in depth. Right now, we will see a cross-section of a single Leopard element at 125 Hertz. And as we saw before, it's essentially omnidirectional for reasons that we discussed. But watch what happens if I start to string multiple of these elements underneath of each other. Every time that I add an element, the beam gets squashed, the beam gets narrowed, and the more elements I add, the narrower the beam becomes. So you can see that at low frequencies, that it's primarily the length of the physical array that is in charge of determining the overall width of the vertical beam. So it's going to be balancing X against beam narrowing in the low end as a function of line length versus beam spreading at the very high frequencies where our line array elements are at their narrowest, and it becomes a matter of point and shoot. Now, talking about those narrow coverage angles, this of course determined the maximum splay that we can introduce between adjacent loudspeaker elements, because we do not want to risk underlap between adjacent line array elements. So from that, you can draw some conclusion. The largest, the flagship model, the Leo M, does not allow you to introduce inter-loudspeaker splay angles of more than 5 degrees, whereas the Lion M loudspeaker, which is the next one in line, allows you to do as much as 9 degrees. By the time you go to LEOPARD, there is a hole which reads 10, which means that you can introduce as much as 10 degrees between adjacent loudspeakers. And for the smallest sibling in the Leo family, you can do as much as 11 degrees. And the 0 degrees is recommended only for transport purposes. Okay, so it's the nominal coverage angle that you typically observe at the highest frequencies that determines the angle that you can introduce between the adjacent loudspeakers. And to show that in action with help of Auto-Splay, I thought it might be nice to go for a moderately sized system and use LEOPARD today to look at that Auto-Splay algorithm. However, there's something that you need to know about LEOPARD. LEOPARD, here you see two enclosures, cross-section. LEOPARD has two links. There's a link in the front, which allows you to introduce splay, and there's a link in the back that allows you to introduce splay. And that technically allows you to introduce an angle of as much as 15 degrees. If you consult the table on the right-hand side on page 28, page 28 of the operating instructions, then you can see that you can introduce as much as 15 degrees, which is not saying that you should, because if you pay close attention to the small print, it also says that splay angles in excess of 11 degrees should only be used under certain conditions, such as trying to avoid a balcony. So it's a prime example of doing research and making sure that we meet all conditions to have a successful design. That being said, we're going to use LEOPARD, but we're not going to use angles of 11 degrees or more. We're going to stick to the rear length, and that will allow us to do 10 degrees at most. So, in order to do that, there's a couple of things that I would like us to discuss about, because we're about to use Auto-Splay to design an array, and that means that that array is going to live at a certain point in space. This is a cross-section. We have a stage over here. We have a security barrier over here, and this is the range that we want to cover. VBOT is a term that we use to designate the start of coverage. It's an abbreviation which stands for vertical bottom, whereas VTOP is a designation that we use to is an abbreviation that we use to designate the end of coverage. It's vertical top. It's where coverage should stop. This line is drawn at ear height, assuming a standing audience, so it's 1.7 meters high, and we want to cover from vertical bottom to vertical top using the Auto-Splay feature. And that means that whatever array we end up making needs to have a certain array splay to accommodate the required vertical coverage target. This is the slice that we want to illuminate with sound, if you will. And a key concept in there to be mindful of is what we call range ratios. And by range ratios, we essentially mean what is the ratio of the distance from the array to the step or the end of coverage, and what is it, how does that relate to the distance from the array to the start of coverage. So that's an elementary fraction. That is the distance to the end of coverage divided over the distance to the start of coverage, because that will give us an indication of the amount of steering that we need to achieve with our array. And we refer to that as range ratios. So let's go to the map file that I prepared, and over here we have that same map file that you just saw in the presentation. And imagine that somebody says the line array has to live in space at where we see that small point. Now, why do I start with that small point? Because that small point happens to be an MM4, which is about the smallest loudspeaker Meyer sound manufactures, and it comes very close to an omnidirectional source. Because I also want to talk about range ratios. If you had to eyeball this from where the line array will live in space to vertical bottom with respect to vertical top, if you had to eyeball that, does that look like a 2-to-1 ratio where this is 2 times longer than the other section? Does this look like 2 times longer to you? I don't think so. So why don't we try to get a better understanding of that? Over here we have a virtual an architectural aid. A visual architectural aid. I'm gonna select that, and I'm gonna draw some lines. So I'm gonna draw a line from that point in space to the first row, which lives over here. And I can click that line segment, and if I right click, I can see the properties of that line segment, and it informs me that this is a distance of about 7 meters. So I'm going to help myself, and I'm going to write that this is about 7 meters, just as a friendly reminder. Okay, that's 7 meters. Now I'm going to take another visual architectural aid, and I'm going to draw a line from that same point to the last person in the audience. I'm going to select that line as well. I want to see its properties as well. And let's get a number on the length of that line. And according to this dialog, it's about 30 meters. So I'm going to bring up a way to remind myself of this, that what we're looking here at, that's about 30 meters. So the range ratio that we're looking for is going to be 30 divided over 7, which is roughly 4-to-1, if I'm not mistaken. I mean, 28 over 7 would be 4. So we're looking at a ratio of roughly 4-to-1, or 4.21 to be more precise. Okay. So what is that in decibels? Well, that's an easy conversion. I will save you the trouble, but this is basically what we're looking at. So we're dealing with a 4-to-1 ratio, or close to, and that means that we're looking at a 12 dB challenge. Let's see if that is the right order of magnitude. So now comes the omnidirectional source. Let's look at our MM4 at 125 Hertz, and let's do a picture. Well, it's safe to say that that is omnidirectional. And if we call, let me fix this. Okay, I don't want you. Cancel. Oh, stop being bossy. Okay. So, let me fix that in another way, because I need the drawing capability. Okay, so there we go. Okay, so if we call this color transition, wrong tool, if we call this color transition, which is roughly where the audience starts, if we designate that as 0 decibels, we can start counting. This would be -3. This would be -6. This would be -9 with 3 dB per color division. And this would be -12 by the time we make it there. So we can clearly see that for an omnidirectional source, that range ratio of 4-to-1 for an omnidirectional source will translate into a 12 dB drop in level, which for most people is 6 dB more than we're willing to accept. We want to come up with a system that keeps that level drop over distance in 6 dB, preferably less, and that means that we need about 6 decibels of stirring. We need to somehow point and shoot the array in such a way that we can decelerate that 12 dB drop in level and bring it closer to something like 6 decibels. And Auto-Splay is going to help us in the process. So I'm done with this omnidirectional source. I'm going to go to my layers. I'm going to hide the omni layer, and I'm going to unhide the leopard array. So there's a leopard array, and right now I just dropped it into space. It's not being pointing anywhere. In fact, if I were to show you a prediction of 1 octave centered at 4 kilohertz, it's safe to say that it's going in the wrong direction. That's not where the audience is. And the question becomes, how am I now gonna use the Auto-Splay feature in MAPP XT to send that sound where it needs to go, which is in the audience and not on the rear wall. In order to do that, we need to draw our audience plane, which is an architectural 8, and we need to activate it as a listening plane. So, how do you introduce an architectural visual 8 to begin with? Well, there's 2 ways of doing it, okay? And for that, I'm going to quickly go to a different keynote. I'm going to go to this keynote, okay, and show you the options. When you insert an architectural visual 8, you can do it by entering the first point, X and Y coordinates, and entering the second point, X and Y coordinates. The other option is that you only enter the first point and then use polar coordinates to determine the direction and the length of the line segment, and that is another way how you can draw that line. For those that like to use the multi-level visual 8, which is also a feature, there's another way of doing it. This requires you a rangefinder or an inclinometer, and it basically consists of the following exercise. You are over there, you have your inclinometer, you measure the distance and the angle to the first row, and then you measure your distance and your angle to the second row. You enter that into the multi-level visual 8, and then it will draw the line segment. Then it will draw the line segment based on those parameters, which is very convenient for larger spaces. So I'm going to show you the first one, and I'm going to bring up the parameters. So what I ended up doing here is assigning that first point, which is 5 meters, into the audience at 1.7 meters, which is ear height, 1.7 meters, ear height. And now I can either enter the second point manually, which is at 30 meters, same ear height, of course, or I could say I want this stretch to be 25 meters long, and that means that from 5 plus 25 meters, you're going to end up at the same position. Of course, I can now also introduce an angle if I want, and that will introduce a slope using the polar coordinates, but right now I do not want a slope. I want to continue the way we were working. And finally, once you have assigned your audience, okay, let's call this audience, you have to activate it as a listener plane if you intend to use the Auto-Splay feature. So notice what I'm doing. I'm selecting this box and say, use this line, use this architectural visual 8 as a listener plane. And that's all that is required so far. Apply and close. Now, the thing that I need to do is simply select my array and the audience planes at once. I can also drag and select them both simultaneously. And now I can right click, and over here there's a dialog which is called Auto-Splay and Overshoot Adjustment. So, in order to show you in a nutshell what is going to happen, I do not want to see all of those center lines. Okay? So what I'm going to do is I'm going to keep only the top center line, and I'm going to keep the bottom center line, and I want to see what happens in the center of the array. Because I'm going to make a prediction. I don't want you, 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 I don't want you. Okay. So right now we only have a center line protruding out of the top speaker, we have a center line protruding out of the bottom speaker, and we have 2 center lines coming out of the middle because we have an even number of loudspeakers, which means that I cannot produce a center line exactly in the middle of the array. I'm going to select that array, I'm going to select the audience plane, I go to the Auto-Splay and Overshoot Adjustment. A dialog opens up and it shows me that I have 3 parameters to play with. 3 parameters to play with. We'll get to the aiming factor during the course of this webinar. There's 2 constraints over here. There's the constraint, what is the smallest splay limit that I'm willing to use, and there's the constraint, what is the largest splay limit that I'm willing to use. Okay, we always recommend at least half a degree. 0 degrees is recommended for transport, and that means that I'm going to stick with the half degree. But what about the largest splay limit? Well, for that we will have to consult our chart, or we will have to consult our operation instructions, or we have to consult our rigging guide, because if you're a leopard, then 10 degrees on the rear link is the maximum recommended splay, for reasons that we discussed earlier. So, even though I'm fully aware that leopard offers as much as 15 degrees of splay, if you use the front link, that is only intended for certain conditions. I'm not going to exceed the 10 degrees, which is recommended as per user guide. And that is all it takes. Aiming factor 0, at least half a degree, at most 10 degrees. If I press Auto-Splay, 3 things are going to happen. The top speaker is going to aim at vertical top, the bottom speaker is going to aim at vertical bottom, and the middle of the array is going to aim at the middle of the audience, because notice that where the middle speakers in the array are pointing is right in the middle, halfway through the audience. There's a question in the chat box. Yes, sir. How can I help you?
Can you hear me?
Yes, I can hear you.
Which parameters change when I increase the target zones? Because I didn't observe any changes.
No, because we yet have to discuss target zones in the next 15 minutes. Okay. So we're not there yet.
Okay, thank you.
Okay, you're welcome. So what happened? The top speaker aims at the last row, the bottom speaker aims at the first row, and the center of the array aims in the middle. And that is what the Auto-Splay algorithm will do time and again in the current under the current constraints, which is a smallest splay limit of half a degree and the largest splay limit in correspondence with the documentation of 10 degrees and an aiming factor of 0. It will send the top speaker to the last row, it will send the bottom speaker to the first row, and it will send the middle of the array to the middle of the audience. And if we were to look at a prediction, it would look the following way. So there we go. Let's start counting some colors. If we were to designate the transition between lime and green, if we were to designate this 0 decibels, then by the time I'm over here, where we see the next color transition, I will have lost 3 decibels, and by the time that I'm over here, I will have lost another 3 decibels, and by the time I make it to the last row, which is over here, sorry, I need to write that differently. By the time I make it to the last row, which is at our destination, I have lost another 3 decibels, and that is 3 decibels more than my liking, which brings us to overshoot. Why is overshoot mandatory? Why do I have a 9 dB drop front to back when I anticipated a 6 dB drop? Well, that has to do with the following. Okay, that has to do with the following. I'm going to clear this. I'm going to select our array. I'm going to go to the properties of our array. Select the array. I'm going to go to the array properties. And let's look at the splays that we currently have. The splays that we currently have are shown in this column. This is the column that shows us the splay angles between adjacent enclosures. And here's what I propose. Here's what I propose. Let's turn on those center lines. Let's hide those guys. I don't want to see those lasers protruding out there. And I only want to see the contribution of these 3 speakers. So I'm going to solo them, and I'm going to turn on the master solo. Let's look at those 3 speakers. So we're only seeing the top 3 speakers, okay, of which the uppermost speaker is touching down at the end of coverage, the way we instructed the Auto-Splay algorithm to resolve that. I would like to point out that these top three speakers, all have the same splay angles. If you pay close attention to these three speakers, you will notice that they all have the same inter-element splay angles. So for all intents and purposes, this is a symmetrical portion of the larger array. And let's see whether that is true. And there you go. Now notice that this is a perfectly symmetrical shape. I call this the tip of the flame. But notice where the tip of the flame touches down. The tip of the flame touches down, it enters the audience, this is where it touches down. And notice that by definition, 1 box above it, it is marginally softer, because by definition, it is impossible to be equally loud on axis to the last loudspeaker as on axis to the joint custody of the top three loudspeakers. Notice that if we look over here, that there is a difference in level. So that is why overshoot is mandatory. I don't want that top loudspeaker to touch down at the last row. I want the second to last loudspeaker to touch down at the last row. It is as if I want to move this tip of the flame, I want to move it up by one loudspeaker. One loudspeaker based on this prediction. So how do we do that? How do we introduce the overshoot? Okay, here's what we're going to do. I'm done with those three loudspeakers. I'm happy to go back to the entire array at once. So I'm done with those loudspeakers. We go back to the entire array. I want to keep the center line of that bottom speaker, of that top speaker, and the second to last speaker as well, so that we can see what happens. So we still have the bottom speaker going to the first row. We have the middle of the array going to the middle of the audience. And in our initial attempt, we have the top speaker still touching down at that last row. But now we want to overshoot. And this is where the aiming factor comes into play. So I'm going to select both the array and the audience plane once more. Right click, Auto-Splay and Overshoot adjustment. Okay. And this time I'm going to set the aiming factor. And what the aiming factor basically allows you to choose is with how many loudspeakers you want to overshoot your destination. Do you want to overshoot with half a speaker? Do you want to overshoot with one whole speaker, or with 1.5 speakers, or with 2 speakers? Well, based on the previous result, I'm intentionally going to overshoot with a single speaker, knowing that on axis to the top speaker can never be as loud as on axis to the second to last speaker. If I now press Auto-Splay, you will notice that the second to last speaker is now pointing, that the second to last speaker is now pointing at the last row rather than the top speaker. And let's do another prediction. Let's do another prediction. So this is the result with overshooting by one speaker, and I'm as happy as a clam in high tide, because if we repeat the exercise and start counting colors, if we call this transition 0 decibels, because we can, then by the time we hit the next color transition, we will have lost 3 decibels. And by the time we make it to the final destination, which is over here, with one loudspeaker overshooting the final destination, I have met the goal of trying to keep that drop in level, which for an omnidirectional source would have been as much as 12 decibels. We've decelerated that and slowed it down to 6 decibels. We've applied 6 decibels of steering, if you will, by delivering a team effort at the last row. Remember, these people are 4 times more distant. These people are 4 times more distant than those people. And the only way that I can send these people more is by deliberately overlapping adjacent loudspeakers, okay, and turning a solo effort into a joint effort. I need the combined horsepower of overlapping elements, whereas in the front of the audience, I don't need the brute force of multiple loudspeakers, the single contribution, the sole contribution of that bottom loudspeaker suffices over there, which of course gives you that typical progressive shape that we're expected to see for line array elements. So, long story short, we introduced a virtual architectural aid. We activated it as a listening plane, which is important for this to work, okay? We selected the array and the listening plane simultaneously, right-click, Auto-Splay and overshoot, which gives you 3 constraints. The first constraint is the so-called aiming factor, with how many speakers would you like to overshoot? What is the smallest angle that you're willing to use? And what is the largest angle that you're willing to use? Without overshoot, the Auto-Splay algorithm will always send the top speaker to the last row. It will attempt to send the bottom speaker to the first row, and the loudspeakers in the middle of the array end up in the middle of the audience. Depending with how many loudspeakers you overshoot, it will send either the second to last or third to last loudspeaker to the last row. That is the recommended practice. Okay, so there's a couple of things that you need to know about the Auto-Splay algorithm. Right now, our audience plane is level. Notice that if we go to our audience plane, that the angle over here reads 0 degrees. It's a level audience plane. We cannot have audience inclinations that are negative. Anything less than 0, right now it's -1, anything less than 0 will not make the auto shoot work. If I now select both audience plane and the array, there is an Auto-Splay and overshoot. Let's see what happens. Okay, nothing happens. I can set a different parameter. Okay, nothing happens because we have a negative inclination. So you need at least a plane, a listening plane, which is either level or has a positive incline. You cannot have a audience plane which has a negative incline. Which brings us to target zones. Let's give this guy a small increase. Okay, let's do something like this. Now our audience plane is rising as we go from the front to the back at a 3-degree angle. This is the 3-degree angle that we just introduced. Okay. The Auto-Splay will now perfectly work. If I were to select both the array and the audience plane, and then go to the Auto-Splay and overshoot adjustment settings, then without overshoot, it will send the top speaker to the last row. It will send the bottom speaker, send it to the first row, and like before, the middle of the array is going to the middle of the audience. But now I want to show you what target zones will do for us. So here's what I propose. Let's turn on all center lines and not just those in the top and in the bottom. Let's turn on all center lines, okay, including the ones that were previously turned off, so that we see all these lasers protruding out of the loudspeaker. What I can do now is say I want to divide this listening plane, which has been designated as a listening plane. I want to divide it in, let's say, 4 zones. And if I do that, our initial audience plane will be divided in 4 even portions. The moment I press apply, suddenly we see that what used to be a single audience plane has now been divided in 1, 2, 3, 4 even chunks. And the purpose that it serves is that if I want to zone my array in anticipation of air losses, then this is a very easy way that I can see which loudspeakers end up in which zones. So let's introduce the overshoot once more. Okay, let's press Auto-Splay. Okay, let's look at the center lines. And now I can very easily see which loudspeakers land in which zone. So loudspeakers 1, 2, 3 in the bottom go to the first zone. So I would wire those three. I would wire those in the as a single zone. The 3 speakers above that go to zone number 2. Zone number 2. The 3 speakers, 2 speakers above that, they go to zone number 3, and the final 4 speakers, they go to zone number 4. So I got 4 speakers in zone number 4. I got 2 speakers, barely 3, depending on how you count. Okay, let's include that guy over there. So I got 3 speakers over here. I've got 2 speakers over here, and I've got 3 speakers over here. And that helps me guide how to wire the array. And this allows me to use additional processing, for example, to overcome error losses, which is proportional to distance. The further you are away, the more penalty points you get due to error losses. And zoning the array is a justifiable way to try to combat those error losses. Right now we have 4 zones, but there is nothing that keeps me from changing the number of zones. And what is quite cute about that is that I could also set the number of zones. I could also set the number of zones to, let's say, 10 zones. And if I do it to 10 zones, you should be able to appreciate what basically the Auto-Splay algorithm is doing, because the first speaker touches down over here, the second speaker touches down over there, the third speaker touches down over there, and everywhere we've created a zone deliberately, there's a speaker touching down, and that is of course how I get less splay in the top, a team effort to overcome a larger distance, less splay in the top and more splay in the bottom, because using the zones you can now clearly see that this distance is essentially constant when we go from front to back. So that's where your zones come into play for zoning the array in a sensible fashion to give you a degree of freedom in additional processing to overcome phenomena such as error absorption. That brings us to what if I have multiple listening planes? What if I have more than one listening plane? Okay, let's select this listening plane. Okay, and let's make it flat again by taking out the inclination, no zones. Okay, apply close. But what if our zones are what if the first part of the audience is let's say 50 meters rather than 20 meters? Okay, so what if the audience has the following shape? Okay, let's see. Okay, must be doing an operator error. I've got my drawing tool. Okay, I want to draw a line. Okay, so let's go over here. Still no line. Okay. 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 Okay, let me see. Active layer. Okay. So what if we have an audience plane that goes like this? And let's designate each of those as audience planes. So uses listener plane, and we're going to select this one, uses listener plane. Okay. Each of these are now designated as listener plane, including the bottom one. I think it was still designated as listener plane. Yep, it is. So now I have 3 listener planes. So what happens if I now choose my array and all the listener planes at 1 and try to bring up the, oh, it's not there. It's not there. So we cannot use the Auto-Splay algorithm to solve for more than one listening plane. I can use it to choose the array, and I can use it to do that listening plane, or I could choose the array and do this listening plane, and then there's an Auto-Splay, or I could use the array and use the bottom listening plane, and then there's an Auto-Splay option, but I cannot do the array and all listening planes at once. However, there's a very convenient workaround, and that is within moderation, Rather than assigning 3 listening planes, just connect the first row with the last row and make one big happy audience plane. Okay, and let's assign this guy as an audience plane. Okay, the whole stretch, let's assign that as a listening plane, an audience plane. Okay, now we're going to select this guy, which is a proxy for the 3 smaller guys. We select our array, okay, and depending on the settings that you choose, okay, the top speaker will go to the last row, the bottom speaker will go to the first row, and there we go. Let's turn on the center lines. Notice top speaker is going to the last row, bottom speaker is going to the first row, and if we do a prediction, that will be perfectly fine. Okay. If you want, you can do a little bit of overshoot, because you see that we're, again, for reasons discussed before, we're 1 speaker short, but rather than doing 3 separate planes, we can also do a single plane. So let's do another iteration. This time we're going to deliberately overshoot. Okay, and let's do another prediction. Okay, and that is perfectly fine. Okay, so let me go to the list of topics that we were supposed to discuss in an hour. Okay, which is how to determine the loudspeaker coverage angle, which we did. The difference between constant Q and proportional Q, which we did. Beam narrowing, which is a function of line length, whereas the Auto-Splay will take care of the beam spreading by sending the sound where it needs to be. We've looked at display angle options in the Leo family, which is determined by the nominal coverage angle of whatever loudspeaker you're using. We looked at a demonstration with LEOPARD, and we figured out that the Auto-Splay without overshoot sends the top speaker to the last row, the bottom speaker to the first row, and the middle of your array to the center of your audience. How to insert an architectural visual aid, how to activate a listening plane. We looked at the consequences of using listening planes with an inclination that is negative, in which case the Auto-Splay does not work. We looked at target zones, which is a cosmetic tool to help you determine how to wire the array in zones to overcome phenomena such as air absorption. And we looked at the importance of overshooting, because on access to the top speaker can never be as loud as on access to the second to last speaker. And finally, how to go about multiple listening planes, which you can very often just bypass by drawing one large listening plane from the first row to the last row. Okay, before we go to the questions, everything that we just discussed can be found at the Meyer Sound website. If you go to meyersound.com, there is a video section. So let's go over there. Okay, let's go to the video section of the Meyer Sound website. We go to the Meyer Sound website and we go to videos. We'll take you to a different page. And over here, under MAPP XT, okay, under MAPP XT, the first chapter that you will find here is the Auto-Splay chapter, so you can review this at your discretion. If history repeats itself, we intend to upload the recording of this webinar to our YouTube channel. The YouTube channel lives at youtube.com/thinking sound. You can already see that last week's webinar is already there, and this webinar will follow soon. We went a little bit over time. That being said, I'm willing to take a couple of questions, but I do not want to go much longer than this. Okay, so let me stop sharing, and let's go back to the camera. Okay, so I need to see the chat. Okay, I see some good questions. How do you go about doing Auto-Splay for M series? Good question. There is a workaround, and we're preparing a follow-up webinar that is going to look at some more in-depth possibilities and features of the Auto-Splay algorithm. But we're out of time right now, so that we'll have to move forward to a follow-up webinar. Can you share the range ratio dB offset equation? Okay, well, there you go. Okay, I propose you make a screenshot of that. Okay, there's the chart. Okay, that's the chart that I was using. The next webinar will be this Monday, this Wednesday, and same time, same place. So 6 p.m. Central European time, 9 a.m. Pacific time, and it's this Wednesday, and I will be talking about down tilt translation in MAPP. We're not seeing your screen. That's because I'm not sharing my screen. Good catch, good catch. Okay, so there we go. There we go. So now you should be able to see it. Okay. Okay. So that makes it 10 minutes past 7, which is 10 minutes over time. I have no problem with that. But like I said before, the next seminar is going to be this Wednesday, 6 p.m. Central European time, 9 a.m. Pacific time, and we're going to talk about down tilt translation in MAPP. So unless there are any pressing questions, I would like to thank you for your time and patience, and hopefully see you in 2 days from now. Stay safe, stay healthy.